Hey, how's it going? This is my physics HP lab 2, uh, the motion of a falling object. So the introduction for this lab is that we're observing and analyzing the motion of an object that is dropped from rest. And our goal is to compare this observed motion to two computational models that we made, one with the drag and gravity and one with the just gravity or no drag. And we want to note the similarities and differences and analyze both. So the models and physical principles that we used were the two self-created computational models, which have the gravity and the gravity plus drag. Along with this, we use Newton's second law, which is the momentum principle. We're using the position update formula and the velocity update formula. And a preview of our results is that computationally, the position decreases with an increasingly negative slope. So you'll see it curves down. In the observed video, the position graph is slightly offset from the model using drag and gravity, but follows a similar curve. So it's pretty close to the model using drag and gravity. And along with this, the slope of the model using only gravitational force ends at a lower position, but also follows a similar curve or slope. So here's just a preview of the two closed grip models. On the left, we have the one with just gravity, and on the right, we have the one with drag and gravity. So Newton's second law, it relates net interaction with the system to the observed motion or change of momentum. It tells us that F net is equal to mass times acceleration. And from this, we get the position update formula and the velocity update formula, um, which are both used in our calculation loop. So gravitational force is another model or another computational principle that we're using. It tells us that it tells us how the force of gravity, mass, and the gravitational force and the direction of that force are related. And on the bottom, I did a simple derivation of the gravity force on Earth, which ends up being 9.8 newtons per kilogram. And then drag force, we know the force of drag is equal to the proportionality constant of drag times the absolute value of velocity, which is also speed squared, times v hat, which is the direction of velocity. And we also know that net force is equal to the force of gravity plus the force of drag. Our system surroundings and initial conditions. Our system is the black expo marker. The surroundings of that expo marker are the Earth and everything around the expo marker. And the initial conditions are that the mass is 0.008 kilograms. The initial position is 1 meter. Total time is half a second. And the initial velocity is 0. So here's the experiment when we put it into tracker. We see that we have our position versus time graph, which has an increasingly negative slope. And you can see how we track the points as it was going down. Along with this, we have our data on the right side. Here's our glow script code for the model with only gravity. If you look over to our computational loop, you can see that we're calculating F net by multiplying g times the mass of the ball times j hat, so we get the direction of gravity, which is down. And we're plugging that into our Newton's second law position and velocity update formulas. Along with this on the right side, we have our initial conditions. So when we're factoring in gravity and drag, as we said earlier, we know that we can add gravity and drag to get our F net. So we calculate them separately. We get the temporary F net, we get the drag force by using our formula, and then we add them to get our total F net, which is then plugged into our Newton's second law formulas for velocity and position. And on the right, we also have our initial conditions again. And here's a graph of all of the data put against each other. So we can see that the model with the gravity and drag is closer to our observed position. And the model with just gravity, computationally, it ends a little bit lower and it's a little bit off from the data. So we can see that gravity plus drag is a lot more accurate compared to our observed position. And some similarities are just all groups of data follow the same increasingly negative slope. You see like the downward curve. And the differences are in the final position of our data. So why do we use these principles? Because Newton's second law allows us to predict velocity and position between time steps. The drag force equation allows us to understand how drag due to air resistance will affect the way an object behaves when it's falling. And we also just know that drag pointing up and gravity pointing down will cancel each other a little bit, and that'll lead to the object having a slower velocity. So in conclusion, we learned that an object that is dropped will experience the forces of both gravity and drag. The drag will work against gravity, slowing down the velocity of the object. And computationally, the model factoring in drag was much more accurate. And some errors that we possibly had an uneven dropping of the expo marker. We also manually plotted points in tracker, which could have been human error, and we could have had an incorrect reading of distance when calibrating tracker. So what if so we wanted to examine the velocity and time to see if any of them have a terminal velocity. So we can see that in our model with gravity and drag, we do reach a terminal velocity because there's a point where acceleration slows down. or there is no acceleration, so the velocity curves. And on the right, we can see there's no terminal velocity reached. And what does it mean if we started with a negative velocity initially, or it was thrown downward? So to simulate this, we started our velocity with a -1, as we can see on the left computationally, and we find that we still do reach a terminal velocity, a point where acceleration can't increase, so it follows a curved velocity graph.